According to classical physics, atoms, like the hydrogen atom, should not be stable. Given a positively charged nucleus, negatively charged electrons should eventually crash into them. However, hydrogen atoms, like all other atoms, are stable. How to solve this puzzle? The first successful explanation for this stability of atoms is due to Niels Bohr. In 1913, he came up with a very simple model for one-electron atoms like the hydrogen atom, called the Bohr Model. Here's one way to derive it. Let's assume the nucleus doesn't move and it has a charge of Z, plus Z. When the electron is circling the nucleus at a certain distance r, in a stable fashion, the centrifugal force must be equal to the electrostatic Coulomb attractive force in order to yield a stable orbit. The attractive force is 1 over 4 pi epsilon 0, where epsilon 0 is the vacuum permeability. Times Z, nuclear charge, and times elementary charge squared divided by r squared, where r is the radius of the orbit. This attractive force must be equal to the centrifugal force, which is equal to me, the mass of the electron, times the velocity of the electron squared, divided by r, again the radius of the orbit. Now let's make an ad hoc assumption. Let's look at the electron as a wave. We could argue that in order to have a stable orbit, the wavelength of the electrons must be such that the electron does not destructively interfere with itself. What that means is that the length of the orbit, which is 2 pi r, must be equal an integer multiple of the de Broglie wavelength, lambda dB, which is h over me times v. N is an integer, 1, 2, 3, and so on. Rearranging this, we get me v r equals nh bar, where h bar is the reduced Planck constant given by h over 2 pi. And reducing this further to isolate the velocity, we get v equals n times h bar divided by me r. Now let's insert this back into the original force balance equation. The left-hand side remains unmodified. 1 over 4 pi epsilon 0 times z e squared over r squared. On the right-hand side, we get me times n squared times h bar squared divided by me squared times r cubed. We can simplify this. A couple of r's drop out and me drops out once. Next, let's isolate r. We get the following. R equals 4 pi epsilon 0 times h bar squared n squared divided by me times z times e squared. Or, if we insert the values for the natural constants, we get 52.9 picometers times n squared divided by z. This value of 52.9 picometers is called the Bohr radius and indicated by A0. It is a radius of an orbit with n equals 1 in a hydrogen atom with z equals 1. These radii describe the stable orbits where the electron wave does not interfere with itself. the radius grows quadratically with the integer number n and inversely proportional to the nuclear charge. It's interesting that under this ad hoc assumption with a de Broglie wave, not all orbits are stable. Only certain discrete values of r are possible. The orbits are quantized and the orbit radii are quantized. This was a very surprising result and eventually led to the explanation of the hydrogen emission spectrum.